Hi, we present learning 3D representations of objects by derendering, a new method that uses derendering to learn representations of images for use on downstream tasks. Derendering aims to predict physical scene parameters including albedo, geometry, lighting, camera position, and so on from an input image. However, derendering is not typically used as a way to learn representations for use on downstream computer vision tasks. On the other hand, representation learning models have been shown to learn meaningful latent embeddings of images, but do not typically model any scene parameters and instead have been shown to learn other semantic attributes. We observe that recent advances in derendering can be combined with representation learning to create representations that can be disentangled based on scene parameters and effectively used for downstream computer vision tasks. Our contributions can be summarized as follows. First, a general framework for learning physically disentangled features by leveraging derenderers that work without supervision or multiview data. Next, a novel objective called Leave One Out Cycle Contrastive Loss that improves encoding by disentangling the features of physical scene parameters such that they are more useful for downstream tasks. And lastly, empirical results supporting the utility of our learned features. In our approach, we use an existing derenderer to decompose single-view images into geometry, albedo, lighting, and camera position, where each scene parameter is predicted by its own encoder-decoder. A differentiable renderer uses the predicted scene parameters to reconstruct the image. Our goal is to disentangle the features of each scene parameter, so we can then use the most relevant features for a downstream task, such as classification. To improve disentanglement between each feature, we introduce a loss called Leave One Out Cycle Contrastive Loss. The key insight is that we can use the differentiable renderer to render augmentations of the image, where each augmentation differs by a single scene parameter. In our work, we change either the lighting or camera position. We then render the augmented image and re-encode the image. Finally, we compare the features of the original image with those of the augmented image, enforcing the features of the unchanged scene parameters are similar using a contrastive loss. Once we have trained our unsupervised representation learning model using derendering, we can then use the learned features for downstream tasks. To optimize our model, we train on a large dataset of unlabeled images, and use both a reconstruction loss to constrain derendering, and our Leave One Out Cycle Contrastive Loss to enforce disentanglement. We train two models, one on faces and one on cars. We then measure clustering accuracy on downstream identification, recognition, and classification tasks, since clustering directly measures the utility of the learned features. We also attach an MLP for classification, and for segmentation we replace the unit encoder with our feature extractor. Shown here are results for clustering. Compared to popular generative models, the features learned from our approach yield higher downstream accuracy. Next, we look at our results when we attach a trainable component on top of our learned features. While the boosts in performance seen with our method here are less significant than with clustering due to the trainable component, we still see improvements for classification and segmentation. More details are available in our paper. Thank you.